You try to compute this for Q equal to say Sn inverse, and then you will see that it is not same. It is not same only when Q is kind of these objects inverted for a string. So these many elements, for them it is not same. So it is again a direct verification. Nothing is happening much. So this concept is indeed useful. And now, how do we encounter these objects more frequently? That was the point KBS was trying to get at yesterday. So let us do that. Say, I will define this concept, give one example, and then we will pass on to.
You may not complete what you set out to do.
Oh, right. So let me do that. Given an idempotent in infinity, it is similar with a projection. What does that mean? Let, I don't know, F be an idempotent from A infinity, then there exists U in, strictly speaking, you may need to go to matrices, okay? But matrices are okay, you can handle them. So I am just writing A infinity, this is wrong, you may need to go to matrices. Or maybe you do not need to go to matrices. I am not writing the argument, but you do not. So then U belongs to A infinity such that U, if U inverse is a projection. So by this argument you conclude that this element is zero or identity. From that you conclude that F must be zero or identity. So cannot be non-trivial, therefore F cannot be.
How do you see that there is an similar projection?
There is an algebraic formula which I should write down. So you write Z equal to 1 plus E minus E star minus C. This is invertible. R equal to E.
E minus E star.
Sorry, F. R equal to Z inverse, and then P equal to F star R. Really one can interpret all these objects, which I am not doing at this moment. 1 minus P plus F 1 minus. Oh, wait.
So what is P?
This is a projection.
Yeah, what is F?
So F star R.
R is Z minus 1.
Z inverse. Z inverse. R is Z inverse.
R is Z inverse.
And this P is a projection. Yes. This is inverse of that. Okay. Your inverse. It is an algebraic formula which all can verify. Yeah, these things are done in the beginning part of. That completes it, but sort of it is just to motivate this definition. And meaning I do not mind, I like this definition, I believe the purpose of this construction in that paper of one is really tempt people to see what is coming, just to invite you. Therefore, in this talk I should also do that. That's why I did. Now I want to define this concept spectral tuple. A spectral tuple consists of a tuple very similar to the earlier one. Earlier one had an algebra represented in the Hilbert space, a central giant operator which was bounded with compact resultant. This time Same, D is self-adjoint. We do not demand these things to be compact, but we demand bounded, and D has compact resolvent. That means D has a set of eigenvalues going to infinity in absolute value. So D has a set of eigenvalues going to infinity in absolute value. That is the meaning of this. Let us write down the simplest example, which I take A equal to C infinity of S1. This example is very instructive for various reasons. I will come back to this example soon in a few minutes.
A is CS, A infinity is C infinity.
Yeah, meaning I do not really decide in this situation. And D is this operator, D of En is N.
C of S1 or C infinity? What is C infinity?
Smooth functions on the circle. There are smooth functions on the circle. So I should write down.
So not total system.
This is density.
Oh. C infinity.
Yes, this is density system. Point to learn from this definition is really the following, because what was the spirit? Spirit was, as soon as I introduce a concept, maybe you should ask me why did I introduce it or why was it necessary. So this one is really, these objects are more easier to interpret, because if you identify this with this via Fourier transform, then you will realize that if I don't know how to write it, 2 pi I n theta. So if I differentiate this function, so via Fourier transform, if we identify this element with the function here, it is this function. If I differentiate, I do get n times. Therefore, this operator is nothing but this operator. So you can interpret this as differentiation. So the idea is that if you have differentiation, then f, which I wrote down last day, is really this operator sine of v. So it is determined via function calculus or like this. So such objects determine, these objects determine these. Conversely, any such object, kind of if A is separable and so on, comes from this, but we do not see it. It is the result of Baz and Zoom. This shows that if I start with something like that and if I make F, then that will be a freedom module. Conversely, all of them come from something like this in the separable case. And my goal is discussing a slightly more complicated example, because almost 50% of my time is used. So now let us, and so far things were easy, we are going to discuss a slightly complicated example, and that is this framework of compact quantum groups. Unfortunately, I will introduce a concept. For this concept, I cannot give you a kind of binding or motivating reason as I was trying to do in this case. Therefore, it is just a definition. We will interpret this definition, and that's about it. Why do we need this? Becomes a different kind of story. A compact quantum group G, even though I put G, it is not actually a group, is a numerical C star algebra A and A numerical homomorphism from A to A tensor A such that transposal of these sets
This is a special tensor product of C star.
this is a special tensor product. So if I represent A faithfully in a reverse space, I take 2 copies of that, I represent the algebraic tensor product, I complete it with this algorithm. But let us spend some time in understanding meaning of this. So it is this recipe which applies all the time. So how do we interpret or last semester I was teaching measure theory and there was a student, whatever you do, he will ask what does it represent. So what does it represent? So let us take this case. Suppose A is commutative. So if A is commutative, then I know that A equal to C of X for some compact vector space. So